Okay, good morning, y'all. That would be you all or yous, guys, depending on where you're from. We're going to do a little translation problem, virtual memory to physical address to cache lookup problem. And this is a review. This is one that we've done before, but I just thought I'd go through the process again. So we're going to start off at top here, look at the virtual address size, which is 14 bits. Physical addresses are 12 bits, page size 64 bytes. TLB, that would be the translation look-aside buffer, is 16 entries, four-way set associative. L1 cache supports block sizes of 4 bytes, 16 entries, direct mapped. So we've got the TLB here, we've got a piece of a page table here, we've got the cache contents here. So we're going to look at a couple of questions and try to figure this out. So first thing to do is to kind of look at what is the virtual address format. And what I usually do is sketch this out. So I'll just try to do that here. In fact, I better get my glasses on. All right. So we're going to sketch out a virtual address. Now it's given to you right down below as well. But I'm just going to do it here just to give you the broad idea. Virtual address is 14 bits, physical 12, page size 64. So once you have the page size, you can say, well, that's going to imply I need 6 bits because 64 is equal to 2 to the 6th. I need 6 bits for the virtual page offset. So let's just put that down. So the virtual page offset, VPO, would be 6 bits. I'll just put it down that way. That means the virtual page number, which is the rest of the virtual address, is going to be 8 bits. Like that. Now, since we're told that the TLB is 16 entries, what we're going to do now is, in order to look up this, what you can do is either take this virtual page number, use it as an index into the page table directly, but since we have a TLB, what we're going to do first is to take that virtual address, split it up into a TLB index and a TLB tag. So I'll sketch that out this way, and I'll put down the TLB index. And first of all, the index is going to have to index through 4 sets. So I know I'm going to need 2 bits to provide the 4 sets, and then the rest of that is going to be the tag. So this would be the TLBI, and that's 2 bits, and the TLB tag, TLBT, is going to be 6 bits. Alright, so the first thing you're going to do is, when we have an address, we're going to check to see if that virtual page number is already in the translation look-aside buffer, the TLB. If it is, then we're going to be looking to get our page table entry directly from the TLB. What is a page table entry? Well, a page table entry consists of some control information and a physical page number. The physical page number is concatenated onto the VPO to give you the physical address. So what we're going to do then is first of all, look for the index here. We're going to look that up in the TLB. We're going to see if the tag matches just the way we do with the cache. Check the valid bit, make sure it's valid. Then if it is valid, we'll pull out the physical page number and then put it down. So start off with a particular virtual address. I've given you the general outline. So we've got 027C. So C is going to be 0, 0. I'll write this backwards. That's C. 7 is 1, 1, 1, 0. 2 is going to be 0, 1, 0, 0, and the rest zeros. Okay, so that's the binary for 027C. So we already know that 6 bits are going to be used for the virtual page offset, so that would be out to here. And then we know that we're going to have a TLB tag, or TLB index rather. TLBI is going to be here, and the rest of it is going to be tag. So the next thing we would do is we'd look up in the TLBI, we'd say, okay, 0, 1, go to the entry, in the first entry in the table, which is up there. Okay, and we're going to see if the tag matches. Well, we've got a tag of 0, looks like a tag of 02. So do we see a tag of 02? Well, we do have a tag of 03 here, a tag of 02 here, a tag of 04, a tag of 0A. So we do have a tag of 0, 2, but notice that it's not valid. That's interesting. Okay, so it's not valid in the TLB. We do have a tag matching, but the valid bit is 0. So the TLB index we said was a 0, 1. The TLB tag was a 0, 2. And TLB hit is a no. So we'll just go ahead and fill those in. Then we're going to treat this whole thing, since we missed in the TLB, we're going to look at the entire virtual page number. So that would be this whole 8 bits here. And the 8 bits gives me a 0, 9. So I'm going to look up in the page table at a 0, 9, see what I can see. And I see there is a 0, 9 here at this index. We have physical page number 17, and it's valid. Okay, so the VPN is going to be 0, 9. Page fault is going to be no. Physical page number is going to be 17. Alright, so now we're going to look at the physical address format. If the physical page number is 17, then we concatenate that with the VPO to give us the physical address. So the VPO we already said was these lower 6 bits here. So I can copy the physical address format and just put those down directly. Okay, so I just copy these bits down into the physical address. We now take the physical page number, and that makes up the rest of the bits. So we have a 7, 1, which is 7, and a 1, and now we have our physical address in binary down here. Okay, so now we take the physical address, and the physical address is going to be applied to the cache. The cache is now, it has a different model. We have a direct mapped cache. We have a block size of 4 bytes. Okay, if we have a block size of 4 bytes, that means my cache offset is the lower 2 bits. That gives me access to any 4 bytes within the cache line. So this would be our CO right here. And then we have 16 entries in a direct mapped cache. That means there's no associativity, so there's 1 line per set. 16 entries means I need 4 bits to access the 16 entries. And so this is going to be my cache index right there. Sorry, a little messy. And then that leaves the cache tag above that. So the cache tag is going to be the last 6 bits. So we start with the cache index. We go to our cache and we see that I've got an index of F. We go down to F and I see that immediately it's not valid. Alright, so we have our byte offset as 0 in this case. Cache index is F. We see that we go to F there and we see the cache tag. Well, it's not valid, so it doesn't really matter in this case. And the cache hit is no, and the byte returned is nothing. Okay, so if we had, let's say that we had something there. Let's say that for grins, that the cache index instead had been 13. Let's say that this had been a 0 here instead. I'm just going to redo this problem, assuming it could be 0. Let's say that's 13 here, in which case we ended up with this line. Well, in that situation, you would say, oh, okay, I'm in line 13. We would see that it's valid, and you would immediately decide, okay, it's valid. We've gone to the cache 13. I've got to look and see. I'm sorry. Yes. Did I say 13? I gave you the wrong number here. Sorry about that. Make it 14. That's what I meant. 14 would be E right here. So if instead we had a cache index, I'm rewinding a little, if instead we had a cache index of 14, then you're going to be looking at this spot, you're going to be looking at this tag. Now the tag would have to match what this tag is here. So the tag would have to be a 1-3, in which case you look at our tag here and it's not a 1-3, so it would not match in that place. Your tag would have to be 0-0-1. So I'd have to have a tag that looks like this in order for me to hit in this particular place. We're going to just make it up and just say yes, that's what our tag is really, in which case we would hit here. We would then go to byte offset 0, which if you look here we have block offset 0, and you'd say 83. So if we went and redid this problem and we said our cache index was really an E and the byte offset is 0, let's say the cache tag was really in this case a 1-3, and let's say it was a cache hit, and then the byte returned would be our 83. Okay, sorry, that's way at the bottom of the page, but you can see. So I've modified the physical address simply to show what it would look like if it was a cache hit, but the process is all the same. Alright, so that's that problem.